Okay, so I've just entered this Kaggle competition, Google Fast or Slow, Predict AI Model Runtime, and it is a beast. It is a giant monster of a thing. And it took me a long time to really understand what the competition was about. There's a lot of different pieces of information in different areas, like in the overview tab, and there's also a related code base, and there's also a related paper. And I thought what I'd do is I'd try to just explain on a very high level what we're doing in this competition, and hopefully that'll save you having to do that yourself. So that's the objective here. By the end of this video, you should have a deep understanding of conceptually what's going on in the competition. And next time we'll go through how to load the data. That's the idea. Okay, so super high level. Machine learning models, we all know them, we all love them. They kind of look like this when we conceptualize them. You know, you have like an input, and that gets passed to the first layer, which then gets passed to the next layer, and so on. And maybe you have like 500 different layers, which we'll just illustrate like this. And then finally, we get ourselves a nice output, right? Like this is kind of what machine learning models look like. And you know, the input could be something big, like an image, and the output could be something small, like a single scalar, which tells us like, you know, is there a dog in the image or not? And that's kind of what, you know, that's kind of how we conceptualize neural networks. Now, whenever we actually run a neural network, what happens is that it gets transferred into a huge, huge graph of very low-level operations. So like, you know, let's imagine all these layers are like 2D convolutions, right? And if you don't know exactly what convolutions are, don't worry about them too much. They're just a common machine learning operation. We think of layers as being, you know, made up of 2D convolutions, but when you actually dig into it, 2D convolutions are themselves, you know, they are themselves these very complex operations consisting of many, many other smaller, simpler operations, like lots of different like multiplication operations, right? You end up with like single elements from the input being multiplied against single elements in the parameters, and then added, right? Added, the outputs are then added to the bias, and then they're passed through like an activation function. And then ultimately we end up with an output. And in a single convolution layer, this will be happening like hundreds and hundreds of times. So you can imagine that like we conceptualize the neural network as sort of this simple abstraction, but when you actually want to execute that on hardware, you have to break it down into this graph consisting of all these like, you know, thousands of different operations that occur. You know, you'll end up looking at something like this on the actual computer, and this will be done like thousands of times in parallel. And then like a really obvious question comes up, which is how do we convert this high-level idea of a neural network into these low-level sort of machine code operations that actually get executed on a GPU or a CPU or whatever? How do we do that in the most efficient way possible? And that is the question that we're concerned with here. Okay, and luckily, right, we're not given this whole huge broad question. They don't leave us with that very broad open-ended question and then tell us to have a field day. Instead, we're actually asked to tackle a very small subset of this question. The question that we have before us in this competition is, let's imagine we start with this graph already. Someone's already gone ahead and made this graph, right? We want to represent this neural network as a graph. Someone already has gone and done it, and they've done a pretty efficient, good job of it. But there are two questions that are remaining that haven't yet been fully determined. The first question is, how do we lay out the tensors in memory as they pass through the graph? And the second question is, how do we split up the tensors such that we can parallelize them in the most efficient way? Because you can imagine, you know, if this is a very big input, you might have a very large tensor going into the graph. How do we split it up into multiple small tensors that we can process in parallel in the most efficient way, or do we even split these up at all? And these are the two central questions of this competition. Firstly, how do we lay out these tensors in memory? We call this the layout problem. And that's something that you'll be seeing a lot, this word layout, that'll come up a lot here. which is how do we lay out tensors in memory. And the other one is how do we break up tensors so that they're smaller and we can run operations on them in parallel most efficiently. And this is called tiling. And if you read the paper, there are sort of a lot of different things that you can do to optimize these graphs. You can do things like fusing different operations together, but it turns out that tiling and layout seem to be the ones that are the most effective. These seem to give you the most bang for your buck. A good tiling scheme and a good layout scheme, this is what will really make the difference between, like, you know, a slow graph and a fast graph. Okay, but what exactly are tiling and layout? What are these things that we have control over in this competition? Let's start with tiling, because tiling's probably a bit easier to understand. So let's imagine that you have a matrix in memory. So now we have this nice like 5 times 8 matrix, all good, and let's imagine that this is T1 from this graph here. And so what we're about to do is we're about to perform the min operation on T1. And so the most basic thing you do is you could just take this whole matrix, you could load it into the RAM, and then you could run the min operation on the entire matrix, and you'll come up with an answer, which will be 1. But it turns out that the way computers are constructed, they usually have like different kinds of RAM. They have different kinds of memory that they use. And often, what'll happen is you'll have these like big chunks of kind of slower memory that it's slower to read and write from, and kind of smaller chunks of faster memory that it's really fast to read and write from. So depending on the computer that you're running on, it might be more efficient, rather than loading the whole matrix into RAM, into like the big slow bit of RAM, maybe it'd be quicker to split the matrix in half and load each half onto the smaller, quicker memory, and then process, do the min operation on each half independently, and then take the min of mins at the end of that. And maybe that would actually be quicker, right? So rather than doing the whole operation at once in slow memory, you break the operation down into 2 sub-operations, perform them in parallel on fast memory, and then aggregate the result. And then that way you might end up with something that's faster. Okay, and that's actually just tiling. I've just explained tiling. We now understand tiling. So all tiling is choosing how to break up tensors, in the case that breaking them up can give you a performance gain. And obviously, like, usually we're not talking about 5 times 3 matrices. We're talking about tensors of dimension like 5, dimension 4 or dimension 5, and it's more like, 128 times 128 times 512 times like 256. So like giant, huge tensors. Okay, so like in those cases, you can imagine that tiling might become quite important. You probably get like very, very big performance gains by tiling those huge tensors correctly. But that's all tiling is, really. And in the case of the competition, what Google has actually gone ahead and done is they've got a bunch of graphs for neural networks that are already running on their TPU hardware. And they've tried, for those graphs, they've tried a whole bunch of different tiling strategies. And so, for instance, this tiling strategy here, you could describe this tiling strategy by talking about the different dimensions and talking about the sort of the largest tile that's allowed on each dimension. So in this case, dimension 1, which is the rows, it has, dimension 1 has a max tile of 4. And every time that you hit dimension 1 and you get more than 4, you break that off into a new tile. Sorry, and that's actually dimension 0. And dimension 1 has no restrictions on tiling whatsoever. So we could just put a 0 there to say that, the tiling restrictions on dimension 1 do not exist. So that's how you could sort of describe this particular tiling strategy. Obviously, there would be like many different kinds of tiling strategy that you could pick. And the way that they express this in the competition, if you look at the data page, is, yeah, they describe it as having like bounds, right? So we would say that the bounds on dimension 0 are 4 and the bounds on dimension 1 are 0 for that tiling strategy that we've just selected. I'll go into depth about what the data actually looks like in a second, but that's conceptually all it is. Different graphs with different tiling layouts and a runtime for each tiling configuration. And we have to predict which tiling configurations will be faster than others on which graphs. Okay, so now let's talk about layout. Layout's a little bit harder to grasp, but it's also a little bit cooler as well. So let's imagine that we have a 2x3 matrix. Okay, very simple, just 2x3 matrix standard. Now, let's imagine that we want to put this matrix in memory. And we know that computer memory is often linear. And for the sake of this competition, we can always assume that it's linear, which is to say that the memory consists of these long, long rows of just like different numbers. So for our purposes, this is the computer memory available to us. These are all the registers in which you can put a number. So let's go ahead and do that. So 2, 5. Okay, so that is one way that you could store this in computer memory. Now, you'll notice, interestingly, that the way that I've chosen puts the rows closer to each other. So 2, 3, and 4, they're sort of contiguous in memory. And the same for 1, 2, and 5. But it actually splits the columns up. So this 2 is actually pretty far away from this 1, which conceptually maybe it should be closer to. And again, the 3 is kind of far away from the 2, and the 4 is pretty far away from the 5. Okay, but let's imagine that we had an operation that we wanted to perform that was really concerned with the columns of the graph. To make that operation run really fast, it might be better for us to lay out the matrix in a different way. Right? It might behoove us to lay it out so that all the columns were close to each other. So instead we'd go 2 and then 1, and then 3 and then 2, and then 4 and then 5. And this new layout, this one puts the columns close to each other, right? 2 and 1, 3 and 2, 4 and 5. Okay, it turns out I can't type. That's great. Love that for me. 4, 5. Okay, cool. So like these are two different ways that you could lay out this matrix in memory. This one makes it easier to do things with rows. This one makes it easier to do things with columns. You can imagine that if we had like a tensor of dimension 3 or 4, you can imagine that, you know, it starts becoming quite important which rows, which columns, you know, which dimensions we put next to each other in memory, because it depends, those dimensions are going to have the same operations performed on each other. So for instance, like, let's imagine that you're putting in an image input into a neural network, which has like a batch size of like 64, right? That's going to be a 4-dimensional tensor. And the dimension that probably isn't that important is the batch dimension, right? The batch dimension, things will be done in parallel over that dimension, but you're not going to have operations that like compare different elements from different batches. So you can imagine that you wouldn't really care about how contiguous different batches were. You'd want to spread the batches out as far away from each other as possible, and maybe keep the other dimensions closer to each other. Okay, and that's what layout is concerned with. There's a concept in this storage called majority, and we say that dimensions have majority if they are more contiguous than other dimensions. So in this case, the 0th dimension, which is the rows, that has more majority in the first layout, and the first dimension has majority in the second layout because it's closer together. And so layout is concerned with which dimensions do we give majority to. And that's kind of it. So like, you know, you'll be given this graph, and there'll be lots of different ways that you could set out the majority of this tensor. Which dimensions do we want to give majority to? before we pass it into the operation. And the idea is that different layouts, giving different dimensions majority, will have an impact on how fast it is to process this graph. And that's basically all there is to it. So in the same way that tiling can affect how fast the graph works, layout can also affect how fast a graph works. And in the competition, what we'll be looking at is these variables. So for every node in the graph, we'll have these variables which dictate the layout of the input, these variables which dictate the layout of the output. Oh, sorry, output and input are mixed up, sorry. Output is first, then input, and then sometimes when the node itself has a kernel inside it, we can also choose the layout of the kernel. So that's kind of what you can be looking for in the competition, is like how do we choose these variables best? And those are the only two variables that this competition is concerned with. Everything else to do with optimization, we don't have to worry about. We only have to worry about choosing good layouts and choosing good tiling. And to be honest, I feel like it could have maybe been a good idea just to do tiling or just to do layout, because the data's complicated enough already. But anyway, so just to end this video out, just to sort of make all the things that I've been saying in this sort of theoretical way a bit more concrete, we're going to have a look at the data and how the data actually pertains to this. Okay, so we've just got a very basic notebook going here, and all we're going to do is we're going to look at what files are out there. We're not going to load any files, we're just going to have a look at what's out there. Okay, so this is the root of all the data, and we have a sample submission. We know what that is, that's normal, we can forget about that. And then we have these two files, npzall and pb. So data is available to us in two formats, the numpyz format, which contains a whole bunch of numpy arrays, and this contains the runtime data that we talked about. So it contains data about graphs, and then data about different layout and tiling configurations of those graphs, and how long those layout and tiling configurations took to run on those graphs. That's what's in the npzall file. And then the pb file, I believe this is Parquet data, and it contains data about the graphs, the same graphs in the npzall file. And the idea is that there's just like a bit more data about the graphs in this pb folder, but it's also a bit harder to get at. So essentially, like, most of the data that you'll need is in npzall, but when you start getting advanced and start getting to the nitty-gritty, you might be able to collect extra data about the graphs that you can then ingest into your machine learning workflow. That'll maybe give you a bit of an edge. So you can kind of think of this as like basic file, and this as advanced file for when you're deciding to go really crazy. And that being the case, we're just going to ignore PB for now. npzall is all we need. So what's in here? Okay, it just says npz, one of those directories that, like, you know, there's nothing there. And then we have these two things, tile and layout. So this contains graphs with different tiling configurations and their runtimes, and layout contains graphs with different layout configurations in their runtimes. So for starters, let's go ahead and look at layout. Okay, we have these two different folders, NLP and XLA. So NLP and XLA, these are just two different folders which contain different graphs that pertain to different kinds of neural networks. For the sake of actually doing this competition, that's all you need to know. If you actually want to dig a bit deeper, NLP contains different BERT-based models, while XLA just contains different other random models that aren't BERT-based. So NLP models, they'll all kind of look a bit the same, whereas the XLA models will look a bit different. Let's have a look at NLP. Inside we have random and default. Okay, so when generating this data, what the Google scholars did is they chose a bunch of different layout configurations for these graphs at random, and then ran them and then recorded the runtime. So that's what's inside random, is different layout configurations chosen at random. Inside default, they used a more advanced searching mechanism to try to find layout configurations that would actually be like good. And that's how they chose different layout configurations, and then they wrote down the runtimes for those layout configurations. So random, you can expect some pretty wacky configurations in there. default, you'll probably, there'll probably be kind of more similar configurations, and those configurations will probably, they'll probably have like similar runtimes and pretty good runtimes. So let's just have a look at random. What's in random? We have valid, test, and train. This is just like classic machine learning stuff. These are 3 folders. They contain randomly selected different samples from all the random generated layouts and their corresponding graphs. So just like having a look inside train, you'll see that like there are all these different files, and the file names, they correspond to like different kinds of BERT-based models, which we could expect because we're in the NLP version. Okay, and each of these contains an NPZ file, and the NPZ file contains information about the graph and information about the runtime that the graph took and the configuration, the layout configuration the graph had. Okay, and you can see there's a similar thing in test, except the graphs have been like, it looks like they've been like anonymized, and similar thing in valid. The one difference in test is that the runtimes are not given for the test batch. Okay, so that's what's inside NLP. Let's have a look inside XLA. And we're not actually going to look inside these files this time. We might do it next time, but it's going to take too long to do that. XLA, again, you have this random and default. Let's have a look inside the default. Again, train, test, valid. Let's just see train. And again, we have all these different like BERT-based like transformer models. They're all in NPZ files. Okay, so now let's just go back and have a look at tile, for example, for a second. So yeah, these were all different layout configurations. This is different tiling configurations. Tile only has the XLA. It doesn't have an NLP file. And it just has train, test, and valid. Okay, and you might be asking, why don't we have the same file structure here? Why does tile XLA go straight to valid, train, and test? Why isn't there like a default and a random for tiling? Well, it's because for tiling, there are actually far more graphs, and those graphs are much smaller. So for tiling, each graph has been broken down into like a very small subgraph. And if you look at the data, you'll see these graphs are much smaller than what you'll find in the layout file. And there's also like way, way more of them compared to the layout file. So in layout, you've got like in tiling, you've got tons of small graphs. And in layout, you have a smaller number of very large graphs. The thing that this means is that for every graph in tiling, they can pretty much exhaustively try every single reasonable tiling configuration. However, for the larger graphs in layout, it was impossible to try every single possible layout configuration for every node in every graph, right? You can imagine that's just like a huge, exponentially large number of different configurations that you'd have to try out. Being unable to do so, they just had to sample randomly and then reasonably different layout configurations for the nodes in the graph. And those are the only data points that we've been given. Whereas again, in tiling, they were able to exhaustively try every possible tiling configuration for the little subgraphs that are in that data set. Okay, and that's the data. Hopefully this high-level explanation will give you sort of something to go off, and it'll make it sort of easier for you to understand what you're dealing with. Because certainly when I tried to load this data initially, I was just full of questions, and a lot of it didn't make any sense to me. This competition is really interesting and cool. I really like how wacky the data is. Just a little interesting piece of trivia here. Of all the graph data sets that exist, this one, called TPU graphs, is kind of an outlier in that the number of nodes per graph and the number of graphs is very high in both cases compared to other existing data sets. So, like, it's kind of a cool data set to work with in general if you want to learn about how to do machine learning on graphs. Okay, next time we'll be looking at some of these NPZ files. I'm sure you're all looking forward to that. And otherwise, good luck. Good luck with this monster that you've decided to grapple with. Good luck there. May God have mercy on your soul.